Hershey's Kisses roll off spinning molds wrapped in silver foil by the millions every day. KitKat bars snap together layer by layer with wafers and chocolate precision, while Snickers bars blend nougat, caramel, and peanuts in a seamless flow of automation. Today, we tour the candy factories that turned sugar, cocoa, and engineering mastery into the world's most beloved chocolate treats. Hershey's Kisses are produced at a scale that borders on surreal. Over 70 million of them made every single day. And yet every one of those tiny, foil-wrapped chocolate drops is engineered to be nearly identical. What looks like a simple candy is actually the output of one of the most tightly controlled, high-speed, and precisely automated chocolate molding systems in the world. It all begins with the chocolate itself. The process starts with raw cocoa beans shipped in from West Africa, South America, and Southeast Asia. As soon as they arrive at Hershey's facility, the beans are cleaned, sorted, and roasted in massive rotating drums. Temperature and roast time are calibrated down to the second, typically around 250 degrees Fahrenheit for up to an hour, depending on the bean's origin and desired flavor profile. Once roasted, the outer husk is removed through winnowing, revealing the cocoa nibs, which are then ground into chocolate liquor. This thick, paste-like mixture of cocoa solids and cocoa butter forms the foundation for all of Hershey's chocolate products. Unlike most chocolate manufacturers that use powdered milk, Hershey's incorporates real liquid milk cooked with sugar, creating a unique milk crumb that gives the chocolate its signature tangy flavor. This process, somewhat unusual in the chocolate world, is conducted under heat and vacuum to concentrate the flavors. The milk crumb is blended with the chocolate liquor, extra cocoa butter, sugar, and emulsifiers to achieve a smooth, pourable consistency. The mixture then goes through steel roller refiners that reduce particle size to roughly 20 microns, fine enough that the human tongue can't detect any grit. That silky texture doesn't come from the rollers alone. It's perfected in the conch, a massive, heated mixing chamber that kneads and aerates the chocolate for hours, developing its flavor and removing unwanted acidity and moisture. Before the chocolate can be molded into its iconic shape, it must be tempered. Tempering is the carefully controlled process of heating, cooling, and reheating the chocolate to form the ideal crystal structure in the cocoa butter. This is what gives a Hershey's Kiss its firm snap, glossy sheen, and slow, clean melt. Chocolate is heated to around 115 degrees Fahrenheit, cooled to roughly 82 degrees Fahrenheit, then gently brought back up to 88-90 degrees Fahrenheit. Done correctly, the resulting chocolate flows like lava, but sets with perfect uniformity. The tempered chocolate is held in insulated tanks and piped towards the forming line, where it enters a machine that deposits it into the classic kiss shape. Unlike molded bars or chips that are poured into cavities, kisses are created through a controlled extrusion process. Rows of nozzles deposit precise dollops of chocolate directly onto a refrigerated stainless steel conveyor belt. As the chocolate is deposited, the nozzle retracts while the chocolate naturally pinches off at the tip, forming the conical shape with a pointed top and flat bottom. The belt's temperature and movement speed are tuned to within fractions of a degree and second, respectively. If the belt is too cold, the chocolate sets before the tip forms. If it's too warm, the base spreads and the kiss loses its shape. Dozens of sensors track flow rate, ambient humidity, nozzle pressure, and belt alignment, all to ensure each kiss is formed with millimeter accuracy. Once deposited, the freshly shaped kisses pass through a cooling tunnel, a long chamber filled with chilled, dry air that circulates continuously to remove heat and firm up the chocolate. The temperature drop is gentle enough to avoid condensation, but fast enough to preserve shape and surface gloss. Within 10 minutes, the kisses are fully solidified and ready for wrapping. And the wrapping process is a marvel on its own. Each solid kiss is picked up by a vacuum arm and dropped into a foil wrapping cell mounted on a high-speed rotating carousel. Simultaneously, two materials are fed into the wrapping head, the foil and the paper plume. The foil is drawn from giant rolls of thin, colored aluminum, silver, red, blue, gold, whatever the batch demands, and cut to size in a flash. The plume, printed with kisses or a special message, is fed in sync. The wrapping head folds the foil around the candy in a rapid twist at the base, capturing the plume and sealing the chocolate in a tight, crinkled package. This happens in under 200 milliseconds per piece. One line can wrap over 1,300 kisses per minute. Each wrapped kiss passes through a camera-based inspection system that checks for foil tears, missing plumes, incorrect positioning, or any visual defects. Any kiss that doesn't meet spec is ejected instantly using a burst of air. The rejected chocolate isn't wasted. It's returned to the melt line, filtered and retempered for another run. Quality control continues behind the scenes as well. Batches are tested in labs for moisture content, fat bloom resistance, flow characteristics, and crystal structure. Technicians cut open kisses to examine the cross-section for air pockets, layering inconsistencies, or fat separation. Every adjustment, from belt speed to deposition volume, is logged digitally and traceable back to the exact minute of production. Perfect kisses move along to the counting and packing line. Vibrating chutes and weigh stations organize the candies into precise quantities. Bags are filled by weight, not just count, ensuring that each package contains the promised amount. Nitrogen is flushed into the bags before sealing to displace oxygen and prevent stalling. Sealed bags are passed through a metal detector and X-ray system to catch any foreign particles or anomalies. They're then boxed by robotic arms, stacked onto pallets, and wrapped in heat shrink film for stability during transport. The pallets are scanned and logged into Hershey's distribution system. Each one is barcoded with batch info, production date, facility code, and destination. Finished product is stored in temperature-controlled warehouses, typically held at 60-65 degrees Fahrenheit, with low humidity to preserve quality. From here, the kisses travel across the country or around the world in refrigerated trucks. Delivery schedules are optimized for seasonality. During hot months, extra insulation or direct-to-store shipping is used to reduce the risk of melting. Throughout the entire facility, cleanliness is paramount. All equipment is made from stainless steel and sanitized regularly using food-safe cleaning agents and steam. The production zones are positively pressurized with filtered air to prevent outside contamination. Workers wear full-body suits, gloves, hairnets, and masks, and must pass through air showers and hand sanitizing stations before entering the floor. Foil and plume materials are stored in sealed environments and loaded into machines without human touch. Even the chocolate pipes are cleaned in place between flavor runs, using hot water and detergent cycles that are validated through swab testing and visual inspection. This entire process runs around the clock, often with multiple production lines working in parallel. Each line is capable of making tens of thousands of kisses per hour, all identical in appearance, texture, and flavor. From roasting the beans to twisting the foil, the manufacturing of a Hershey's Kiss is as much a feat of engineering as it is confectionery tradition. What's remarkable is not just how they taste, but how exactly the same they are every time, no matter where you buy them or when you eat them. Behind that small, familiar shape is a chocolate system scaled to near industrial perfection. It's a product of thermal curves, pressure gradients, micron filtering, and synchronized robotics. A Hershey's Kiss may only weigh a few grams, but producing one requires careful orchestration of chemistry, mechanical design, and logistical precision, multiplied by billions. And it all happens quietly, on spotless steel lines, in a factory built to never stop moving. Inside a KitKat factory, chocolate isn't poured, it's engineered. Every bar, with its signature snap and crisp wafer layers, is the end result of a factory process that balances delicate baking with high-speed chocolate molding, synchronized layering, and one of the most visually satisfying enrobing systems in modern candy manufacturing. What looks like a simple chocolate-covered wafer is actually a tightly orchestrated sequence of steps where the biggest challenge isn't just making it. It's making millions of them, perfectly identical, every single day. KitKat starts with the wafer. While most chocolate bars focus on fillings or centers, KitKat's core is a multi-layered biscuit that must be ultra-light, uniformly crisp, and flat enough to stack 3 high without collapsing or cracking. This begins in the bakery section of the factory, where wafer batter is mixed in massive stainless steel tanks. The ingredients are basic: wheat flour, starch, sugar, leavening agents, and vegetable oil, but the ratios are finely tuned to yield a light, aerated texture. Water is added just enough to form a pourable slurry. This batter is piped directly into wafer baking ovens, which look like massive horizontal carousels. Each machine contains 2 rotating drums lined with dozens of waffle-patterned molds. As the drums rotate toward each other, they clamp shut, sandwiching a thin layer of batter between heated metal plates. In just under 90 seconds, the wafer is cooked to a delicate golden sheet. These sheets are just millimeters thick and almost paper-light. The ovens run non-stop, producing hundreds of sheets per minute. The baked wafers exit onto a cooling conveyor, where fans and chilled air reduce their temperature quickly to prevent sogginess. Once cooled, they pass into the layering line, a critical step where the wafers are glued together with chocolate cream. This isn't standard chocolate. It's a specially formulated cocoa-based paste, piped in a fine, even layer between each wafer sheet. 3 sheets are stacked, with 2 thin layers of cream between them. Pressure rollers gently compress the stack to bond the layers without cracking the wafers. One of the more surprising aspects of KitKat production is what the filling is actually made from. In part, it's made of recycled KitKats, the ones that break, misform, or fall short of QA. These rejected bars are ground up into a fine paste and blended back into the chocolate cream used between the wafers. It's a clever, zero-waste feedback loop that both preserves flavor consistency and reduces scrap. In some factories, as much as 10% of the cream layer is made from reprocessed KitKat centers. Once the layered wafer slabs are complete, they pass through a precision cutter. High-speed blades slice the large sheets into individual fingers, typically about 85 mm long and 20 mm wide. Each one is checked by laser sensors for length, straightness, and evenness. If a bar has a slight tilt or crack, it's immediately rejected and fed back into the recycling system. From here, the fingers ride a narrow belt into one of the most iconic stages in the process: enrobing. This is where each finger gets coated in smooth milk chocolate. The chocolate itself has been tempered for shine and texture. It flows at a controlled temperature around 88-90 degrees Fahrenheit, with its cocoa butter crystals aligned for perfect snap and melt. The enrobing machine creates a literal curtain of chocolate under which each bar passes. A wave of molten chocolate washes over the top and sides, while a bottoming roller coats the underside. The excess chocolate drips through a mesh belt, collected below and returned to the circulation tank. Air knives, powerful jets of high-speed air, blow across the moving belt, removing extra chocolate and revealing the shape of the finger while still coating it fully. What's left is a sleek, glossy KitKat bar with clean edges and a uniform chocolate thickness, still warm and soft from enrobing. The bars then enter a long cooling tunnel, usually 20 to 30 meters in length. Inside, temperature-controlled air circulates slowly, gradually lowering the chocolate's temperature to harden it without shocking it. A sudden freeze would lead to bloom or cracking. Instead, the bars cool gently over 8 to 10 minutes emerging with a firm shell that snaps cleanly when broken but resists melting during packaging and transport. By this point, each bar is visually complete, but the process is far from over. At the end of the tunnel, every bar passes through automated quality inspection systems. Cameras and infrared sensors scan each one for chocolate coverage, surface defects, weight, and alignment. Any deviation, even by a fraction of a gram, triggers a rejection system. These bars don't go to waste. They're melted down and fed back into the chocolate tanks to be used in the next batch. Perfect bars continue down the line to the wrapping machines. KitKats are wrapped in a double-layered system, a printed plastic or foil wrapper on the outside, and sometimes an inner paper band depending on the market. Wrapping machines align each bar, fold the film around it, seal it with heated rollers, and apply batch codes and expiration dates using inkjet printers. Each wrapper must align exactly with the printed graphics, a task handled by photoelectric sensors that detect registration marks and adjust feed speeds in real time. From here, the wrapped bars are grouped into multi-packs or boxes using robotic arms. Arms fitted with suction cups or padded claws pick up groups of bars and slot them into cardboard trays at speeds that would be impossible by hand. Each carton is folded, glued, and sealed within seconds, then conveyed to the palletizing area. Palletizing is fully automated. Mechanical lifts and rotary turntables arrange boxes into precise stacks, which are shrink-wrapped and labeled with shipping codes, destination information, and batch traceability tags. These pallets are sent into cold storage warehouses kept between 60-65 degrees Fahrenheit with low humidity to prevent chocolate bloom or degradation. From here, KitKats are loaded into refrigerated trucks for distribution across the country or the world. What makes KitKat manufacturing especially challenging is that it combines the sensitivity of biscuit baking with the demands of chocolate work. Wafer requires dry heat. Chocolate requires cool handling. That means the factory floor must be divided into multiple climate-controlled zones, with airlocks separating baking areas from enrobing rooms. The enrobing room, for example, is kept cool and dry, often around 65 degrees Fahrenheit and less than 50% humidity. Wafer ovens, on the other hand, can reach over 400 degrees Fahrenheit at their cores. Maintaining that balance of heat and chill under one roof requires advanced HVAC systems, multiple pressure zones, and real-time monitoring of air quality. Hygiene is also paramount. All food contact surfaces are stainless steel. Between each shift, machines are taken offline and cleaned in place using foam detergents and pressurized steam. Conveyor belts are modular and easily removed for inspection. Workers wear full-body suits, hairnets, gloves, and pass through sanitizing stations before entering production zones. Metal detectors and X-ray machines sit along the line, scanning both raw and finished product to ensure no fragments or contaminants get through. Each batch of KitKats is logged with data points, ingredient lot numbers, temperature curves during baking and cooling, enrobing weights, wrapping alignment, and output yield. This data feeds into a centralized control system that allows production managers to adjust variables remotely and trace back any defects to their source in seconds. If a wrapper print run is misaligned by even 1 millimeter, the system flags it. If a batch of chocolate cools too quickly and forms the wrong crystal type, the conching or tempering settings are adjusted before the next batch is poured. The result of all this precision is a candy bar that seems effortless. 4 fingers of chocolate-coated wafer that break cleanly and taste exactly the same every time you unwrap one. But under the surface, every KitKat is the end result of synchronized baking, molding, cutting, layering, coating, cooling, scanning, wrapping, and boxing, performed by machines that don't pause, don't drift, and don't guess. From the crisp snap of the chocolate shell to the aerated crunch of the wafer beneath, a KitKat is built on repeatable engineering. It's chocolate and wafer in perfect proportion every single time. Made possible by a factory system that's part bakery, part confectionery lab, and part automated packaging line. Millions are produced daily, and nearly all are indistinguishable from the next. What feels like a quick snack is behind the scenes a precisely manufactured product built by a system that never stops chasing consistency. And it all happens without ever compromising the most important part, the snap. That clean break between fingers isn't just a satisfying detail. It's a signal that the layering was precise, the baking was even, the chocolate was tempered, and the process worked exactly as designed. In the world of candy manufacturing, KitKat isn't just a bar. It's a blueprint. A Snickers bar is a tightly packed engineering marvel. Dense, chewy, crunchy, sweet, salty, and balanced with just enough give to make that signature bite. But making a Snickers at scale isn't as simple as layering some nougat, caramel, and peanuts under a sheet of chocolate. It's a high-speed operation of precisely tuned machinery that replicates that perfect structure. Soft base, sticky center, solid top, millions of times per day without drift. Every layer is calibrated, extruded, and cooled in sequence, and the end result is a candy bar built more like a micro-assembly line than a piece of confectionery. It all starts with the nougat, the foundation of every Snickers bar. Inside the factory, huge stainless steel mixing vats are fed with liquid sugar, corn syrup, milk powder, and a blend of oils and fats. The exact mix varies slightly by market, but the process is the same. The ingredients are heated and blended until they reach a warm, pliable consistency, thicker than frosting, lighter than dough. In some Snickers plants, egg whites or soy proteins are added to aerate the nougat, creating a slightly spongy texture. The whole blend is whipped at high speed to incorporate air, giving the nougat its characteristic softness and volume. Once aerated and cooled slightly, the nougat mixture is pumped onto a moving steel belt through a long rectangular nozzle. This extruder controls the height and width of the base layer down to the millimeter. As the nougat flows onto the belt, a series of rollers level the surface into a perfect slab, flat on top, consistent in density. It begins cooling immediately, traveling through a temperature-controlled tunnel with chilled air circulating above and below the conveyor. This ensures the nougat sets firmly enough to hold its shape for the next step, caramel. Caramel for Snickers is made in high-capacity kettle cookers. Sugar, glucose, dairy solids, and fats are heated to specific temperatures, usually in the 230 degrees Fahrenheit to 245 degrees Fahrenheit range. To control the final texture, it needs to be stretchy, sticky, and able to support whole peanuts without becoming too hard or too fluid. The exact boil point determines whether the caramel will pull or snap when bitten, and that consistency has to be stable across thousands of pounds of product. Once cooked, the hot caramel is poured directly onto the cooled nougat layer using a heated pipe system. A series of spreader blades and vibratory tables help evenly distribute the caramel across the moving slab, creating a uniform layer just a few millimeters thick. While the caramel is still warm and tacky, the next component is added: whole roasted peanuts. Peanuts are roasted off-site, typically using dry air systems, and delivered in bulk. They arrive at the factory pre-sorted by size and quality and are stored in silos until use. As the caramel slab moves under the peanut depositor, peanuts are released in a carefully measured scatter. Conveyor vibrators and guiding rails help control the distribution, ensuring an even coating of nuts without clumping or bare patches. Any peanuts that miss the slab fall through and are recirculated. Once they land in the caramel, they sink slightly and begin to bond as the caramel cools and firms. Now the triple-layered slab, nougat, caramel, and peanuts, must be portioned. Giant guillotine blades drop in quick succession, slicing the continuous sheet into individual bars at exact intervals. These blades are water-cooled to prevent sticking and operate on a feedback loop with laser sensors that track the speed and position of the slab. Each cut is clean, firm, and aligned perfectly with the center of the peanut layer. These cut bars now head into what may be the most iconic part of the process, enrobing. The naked bars enter a chocolate room, cool, dry, and tightly controlled for humidity. Milk chocolate, tempered to 88-90 degrees Fahrenheit, is held in a series of heated tanks with continuous agitation. This chocolate isn't just melted, it's tempered to encourage the formation of type 5 cocoa butter crystals, which ensure a glossy finish and a clean snap. Bars travel into the enrober on a wire mesh belt. As they pass through, a curtain of chocolate pours down over them from above, coating the top and sides. Simultaneously, a bottoming roller ensures the base is fully covered. As the chocolate hits the cold bar, it begins to set immediately. Air knives blow off excess chocolate to prevent pooling and maintain shape. The signature chocolate lines on top of the Snickers bar are formed at this moment too, by a vibration plate or pattern nozzle just before the bar exits the enrobing chamber. Once fully coated, the bars pass through a long cooling tunnel. Inside, chilled air flows over the bars in precise cross-ventilation patterns, gradually bringing the temperature down to around 50 degrees Fahrenheit. This takes about 10 minutes and ensures the chocolate sets firmly without bloom or surface dullness. The bars emerge glossy, uniform, and solid, ready for wrapping. Each bar moves into the wrapping line, where high-speed machines feed printed plastic film from giant spools. As bars arrive, a synchronized roller wraps the film around each bar and seals the ends with heated jaws. A photo eye sensor ensures the printed graphics align correctly with the bar. Misaligned wrappers are automatically corrected mid-run by adjusting film feed speed. At full speed, the wrapping machine can process over 600 bars per minute. Wrapped bars pass through a metal detector, then onto a weight check scale. Any bar that's too heavy or light is automatically diverted. Accurate weight ensures every bar contains the right balance of caramel, nougat, and peanuts, and also meets legal labeling requirements. The wrapped bars are then grouped into boxes or trays depending on final destination. Robotic arms or automated pushers organize them into shipping units. Boxes are sealed, labeled with date codes, batch numbers, and facility identifiers, then stacked onto pallets. Palletizing is handled by robotic forklifts that stack, wrap, and barcode the loads before moving them into cold storage. Warehouses maintain temperature and humidity controls to preserve product integrity during transit. Meanwhile, every batch of Snickers is tracked digitally through a manufacturing execution system. From the moment a peanut is roasted to the second a bar is boxed, each component is scanned, time-stamped, and logged. This allows full traceability in the event of any issue and provides a goldmine of data for optimizing production. Line managers can monitor caramel viscosity, cutting pressure, chocolate flow rate, peanut density, and dozens of other metrics in real time. Factory hygiene is unrelenting. All food contact surfaces are stainless steel or non-porous plastic, cleaned and sanitized daily. Equipment that handles caramel and chocolate is cleaned in place with hot water flushes and detergent cycles. Air is HEPA filtered and exchanged multiple times per hour in the production zones. Workers wear protective clothing, pass through sanitizing gates, and must adhere to strict hand washing and allergen controls. Peanut handling areas are physically separated from other lines to prevent cross-contamination. Even the factory layout is designed to keep product moving in a single, linear direction, from raw material intake to finished goods. This minimizes handling, reduces contamination risk, and allows for streamlined automation. Conveyor belts are staggered by elevation and angle to optimize speed and reduce manual touchpoints. Every sensor, cutter, heater, and cooler is synced to the master control system so that timing between each step is tight enough to maintain throughput but loose enough to allow for mechanical resets and cleaning. The result is a product that tastes chaotic but is built with precision. That satisfying bite, where teeth hit chocolate, then peanuts, then soft caramel and airy nougat, is only possible because each layer was placed with absolute consistency. At peak output, a Snickers plant can produce well over 400,000 bars per shift, each identical in composition, shape, and texture. And while the final product feels casual, almost simple, the process behind it is anything but. It's a bar made by layering viscosity, by tempering flow rates, by tracking shrinkage curves in caramel and chocolate alike. The factory doesn't just make candy, it makes edible geometry. Nougat is aerated to hold just the right volume. Caramel is tuned to stretch but not stick. Chocolate is crystallized with surgical precision. And peanuts, they're roasted, sorted, and scattered with just enough randomness to feel natural, while still passing digital pattern checks. In a modern Oreo manufacturing facility, key dry ingredients are delivered in bulk, often by rail cars or food-grade trucks, and are pneumatically conveyed into large storage silos made of stainless steel or epoxy-lined carbon steel. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, they are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold, and they won't disperse evenly. Too hot, and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey: shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line: forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small, motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of 2 primary components: a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase: baking. Meanwhile, the excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from overprocessing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, the conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts, equipped with vision systems, scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds. Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronized parts of the process: sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual-lane conveyors that separate and feed cookies into two different orientations: bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, a rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single-serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis, and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. Pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal. The process begins with the sourcing of raw ingredients, including hazelnuts, sugar, cocoa powder, palm oil, skim milk powder, and vanillin. These ingredients are delivered to Nutella factories in massive quantities, requiring large-scale handling infrastructure. Hazelnuts, one of the key components of Nutella, are often sourced from Turkey and Italy, two of the largest hazelnut producers in the world. Upon arrival at the factory, hazelnuts are stored in enormous silos or temperature-controlled storage rooms to maintain their freshness. The silos are made of food-grade stainless steel and designed to protect the nuts from humidity and contamination, while allowing for precise dispensing into the production line. The first step in processing the hazelnuts is cleaning. Hazelnuts arrive in bulk shipments, often mixed with debris such as shells, stems, and dirt. To address this, the factory uses a series of cleaning systems that include vibrating screens, air classifiers, and magnetic separators. The vibrating screens shake the nuts to separate them from larger debris, while the air classifiers blow away lightweight impurities like husks and dust. Magnetic separators are also used to detect and remove any metallic particles that might have entered the shipment during harvesting or transport. Once cleaned, the hazelnuts undergo visual inspection using high-speed optical sorting machines equipped with cameras and sensors. These machines identify and remove any defective hazelnuts, such as those with discoloration, cracks, or signs of mold. After cleaning, the hazelnuts move to the roasting stage. Roasting is a crucial step in developing the rich, nutty flavor that characterizes Nutella. In the factory, this is achieved using massive industrial roasting ovens. These ovens are designed with rotating drums or conveyor belts to ensure even roasting. The temperature is carefully controlled, typically ranging between 280 and 320 degrees Fahrenheit, depending on the size and moisture content of the hazelnuts. Sensors monitor the temperature and time to ensure consistency, as over-roasting can lead to bitterness, while under-roasting can result in a lack of flavor. The entire roasting process is automated, and the equipment is designed for continuous operation to handle the high volume of hazelnuts required for production. Once roasted, the hazelnuts are transferred to grinding machines. These machines are equipped with heavy-duty stainless steel blades and rollers that crush the nuts into a fine paste. The grinding process occurs in multiple stages, with each stage further reducing the particle size of the hazelnut paste. In the initial stage, the nuts are coarsely ground into a chunky paste. In the subsequent stages, the paste is refined into a smooth consistency, with particle sizes measuring less than 30 microns. This ultra-fine grinding is essential for achieving Nutella's creamy texture. The equipment used in this process, such as colloid mills and ball mills, is highly specialized and designed to operate under high pressure and at precise speeds. The resulting hazelnut paste is collected in large stainless steel tanks, where it is stored at a controlled temperature to preserve its flavor and consistency. While the hazelnut paste is being prepared, the other ingredients are processed in parallel. Sugar, which provides sweetness to Nutella, is delivered to the factory in bulk containers or tankers. Upon arrival, the sugar is unloaded into silos, equipped with pneumatic conveying systems. These systems use air pressure to transport the sugar from the silos to the milling area, where it is ground into a fine powder. Industrial sugar mills are used for this purpose, and the grinding process ensures that the sugar particles are small enough to dissolve uniformly in the mixture. The factory also incorporates sieving systems to filter out any impurities or oversized sugar particles before they proceed to the blending stage. Cocoa powder, another key ingredient, undergoes a similar process. The cocoa powder is stored in sealed silos to protect it from moisture and contamination. Before being added to the Nutella mixture, the cocoa powder is sifted through vibrating screens to break up clumps and ensure a fine, even consistency. This step is crucial for achieving the smooth texture of the final product, as any clumps could create inconsistencies during blending. Palm oil, which gives Nutella its creamy consistency and prevents separation, is stored in large, temperature-controlled tanks. These tanks are equipped with heating elements to keep the oil in a liquid state, as palm oil tends to solidify at room temperature. The oil is pumped through insulated pipes to the mixing area, where it is carefully measured and added to the blend. The precise control of temperature and flow rate is essential to ensure that the oil integrates smoothly with the other ingredients. Skim milk powder, which adds a subtle dairy flavor and contributes to the creamy texture of Nutella, is stored in sealed containers or silos to prevent exposure to air and moisture. Before being used, the milk powder is sifted and screened to remove any lumps. Factories use advanced pneumatic conveying systems to transport the milk powder from the storage silos to the mixing area, ensuring that the ingredient is handled efficiently and hygienically. The blending process is the heart of Nutella's production, where all the prepared ingredients come together to form the final product. The blending tanks used in Nutella factories are massive, often with capacities of several thousand gallons. These tanks are equipped with high-speed agitators and temperature control systems. The hazelnut paste, sugar powder, cocoa powder, skim milk powder, palm oil, and vanillin are added to the tank in precise proportions, which are controlled by computerized dosing systems. These systems are programmed to weigh and dispense each ingredient accurately, ensuring consistency across batches. During blending, the mixture is heated slightly to help the ingredients combine more effectively. The temperature is carefully monitored, as excessive heat could alter the flavor and texture of the product. The blending tanks are designed to ensure even mixing, with agitators that create a vortex to incorporate all the ingredients thoroughly. The result is a homogeneous mixture with a smooth, creamy consistency. Once the blending process is complete, the mixture undergoes a refining stage. Refining is a critical step that ensures the final product is free of any graininess. The refining process takes place in multi-stage roller mills, which are equipped with heavy-duty steel rollers. These rollers apply immense pressure to the mixture, reducing the particle size of any remaining solids to less than 20 microns. This process not only enhances the texture of Nutella, but also improves its spreadability. The roller mills are fitted with precision sensors that monitor the pressure and temperature during refining, ensuring optimal performance. After refining, the mixture is transferred to the conching stage. Conching is a process borrowed from chocolate manufacturing and involves agitating the mixture in large, heated tanks for several hours. This process helps to further smooth the texture and enhance the flavor of the spread by allowing volatile compounds to evaporate and by evenly distributing the fats and solids. The conching tanks are equipped with paddles or rollers that knead the mixture continuously. The temperature and duration of conching are carefully controlled, as overconching could negatively affect the spread's consistency. The finished Nutella is then pumped into holding tanks where it is kept at a controlled temperature until it is ready for packaging. These tanks are equipped with agitators to prevent separation and maintain the spread's uniformity. Before the Nutella is packaged, it undergoes a final round of quality control. Samples from each batch are tested for flavor, texture, color, and viscosity. The factory uses advanced laboratory equipment such as viscometers and spectrophotometers to ensure that the product meets the company's stringent standards. Any deviations from the desired specifications are identified and corrected before the product proceeds to the packaging stage. Packaging is the final step in Nutella's production process, and it is carried out with the same level of precision and efficiency as the earlier stages. The spread is pumped from the holding tanks into automated filling machines, which dispense precise amounts of Nutella into jars. The filling machines are equipped with high-speed nozzles that can fill hundreds of jars per minute. Each jar is made from food-grade plastic or glass and arrives at the factory pre-sterilized to ensure hygiene. The jars are sealed with tamper-proof lids, which are applied and tightened using automated capping machines. Once the jars are sealed, they are conveyed to labeling stations, where Nutella's iconic branding is applied. The labels include important information such as the lot number, production date, and expiration date, which are printed using high-speed inkjet or laser printers. After labeling, the jars are inspected by vision systems that check for defects such as misaligned labels or damaged seals. Any defective jars are automatically removed from the production line. The jars are then packed into cardboard cartons using robotic packing systems. These systems are programmed to arrange the jars in specific configurations to maximize space and protect the jars during transportation. The cartons are sealed and stacked onto pallets using robotic palletizers. The pallets are then wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. The entire packaging process is designed for high efficiency, with minimal manual intervention and maximum output. Throughout the factory, automation plays a key role in maintaining efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems are used to monitor and control every aspect of the production process. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. The factory is also equipped with advanced robotics and machinery that ensure smooth operation, from ingredient handling to final packaging. Hygiene and safety are top priorities in Nutella factories. Production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Air filtration systems maintain a clean environment by preventing airborne contaminants from entering critical zones. Employees follow strict hygiene protocols, including wearing protective clothing and washing their hands regularly. The factory is regularly inspected to ensure compliance with international food safety standards, guaranteeing that every jar of Nutella is safe for consumption. This intricate, highly automated process ensures that Nutella is consistently smooth, flavorful, and delicious, meeting the high expectations of its millions of fans worldwide. Every step, from the handling of raw ingredients to the final packaging, is a testament to the engineering and precision that go into creating this beloved spread. The result is a product that continues to delight consumers, one jar at a time. Peanut butter, a staple spread beloved worldwide for its creamy or crunchy texture, requires a sophisticated and highly organized manufacturing process to meet the demand for consistent quality and flavor. Behind every jar of peanut butter is an intricate factory process that starts with the raw peanuts and ends with precisely packaged jars ready for distribution. Let's take an in-depth look at the factory production process, exploring the machines, systems, and engineering techniques that make it all possible. The process begins with the sourcing of raw peanuts. These peanuts are typically grown in countries like the United States, China, India, and Argentina, which are among the largest producers of peanuts globally. Peanuts are harvested in vast quantities, cleaned and dried at their source before being shipped to peanut butter manufacturing facilities. Factories require a consistent supply of high-quality peanuts, and to ensure that the raw peanuts are often tested upon arrival for size, moisture content, and overall quality. This ensures only the best peanuts are used for processing. Upon arrival at the factory, peanuts are stored in massive silos or bins designed specifically for food products. These silos are constructed from food-grade stainless steel or coated steel to prevent contamination and ensure proper hygiene. Inside the silos, the peanuts are protected from moisture, pests, and temperature fluctuations. These storage systems are equipped with conveyor systems that efficiently transfer peanuts from the silos to the initial cleaning and processing stages. The first step in processing peanuts is cleaning. Even though peanuts are partially cleaned at their source, factories implement a rigorous cleaning process to ensure no foreign materials or impurities remain. Vibrating screens are used to remove debris such as dirt, stones, and small sticks. Air classifiers blow air through the peanuts to remove lighter debris such as peanut skins or husks. Magnets are also employed to extract any metallic impurities. Optical sorting machines equipped with cameras and sensors scan each peanut as it moves along a conveyor belt, automatically removing any defective peanuts, including those with discoloration, mold, or deformities. After the cleaning process, the peanuts proceed to the roasting stage. Roasting is a critical step in peanut butter production, as it develops the rich, nutty flavor that defines the final product. Factories use industrial roasting ovens to roast the peanuts at controlled temperatures. These ovens come in two main types: batch roasters and continuous roasters. Batch roasters are used for smaller production lines, while continuous roasters, which use conveyor belts to move peanuts through a heated chamber, are used for larger scale operations. The temperature in these roasters typically ranges from 300 to 350 degrees Fahrenheit. The roasting process is closely monitored with temperature sensors and automated control systems to ensure the peanuts are roasted evenly. If some peanuts are over-roasted, they can turn bitter, while under-roasted peanuts may lack flavor. The level of roasting can also be adjusted depending on whether the final peanut butter will have a mild or more robust taste. Once roasted, the peanuts are cooled to stop the cooking process. Cooling is achieved by passing the roasted peanuts through chambers with powerful fans or cool air blowers. This step is crucial because it prevents the peanuts from continuing to cook, which could lead to inconsistencies in flavor. Some factories also use a water spray system to rapidly cool the peanuts, though this is less common as it can add moisture to the product. The cooling systems are designed to operate continuously to keep pace with the output of the roasting ovens. With the peanuts roasted and cooled, the next step is to remove their skins and separate the kernels. Skin removal is done using blanching machines. These machines have rotating drums or abrasive rollers that rub the peanuts, causing the thin outer skin to flake off. Some systems use steam blanching, where the peanuts are exposed to high-pressure steam to loosen the skins before mechanical removal. After blanching, the peanuts pass through air classifiers that blow away the loose skins, leaving behind clean peanut kernels. Factories also use gravity separators to sort peanuts by size and density, ensuring that only uniform peanuts proceed to the grinding stage. Before grinding, the peanuts are inspected again for quality. This is done using high-speed optical sorters that ensure any remaining defective peanuts are removed. Factories often have automated weighing and proportioning systems at this stage to determine the exact amount of peanuts needed for each batch. This level of precision is crucial for maintaining consistency in the flavor and texture of the peanut butter. The grinding process is the heart of peanut butter production. The roasted peanuts are fed into industrial grinders, where they are crushed into a fine paste. This process happens in multiple stages, beginning with coarse grinding and followed by finer grinding. The equipment used for this includes hammer mills and roller mills, which are specifically designed to reduce the peanuts into small, uniform particles. In many factories, the particle size is reduced to less than 20 microns, which is smaller than the diameter of a human hair. Achieving such a fine consistency is essential for the creamy texture that many consumers expect from peanut butter. For crunchy peanut butter, the process is slightly different. In these cases, a portion of the peanuts is coarsely ground and set aside before the final blending stage. These larger peanut pieces are later mixed into the smooth paste to create the characteristic crunchy texture. To prevent the peanut butter from separating, stabilizers such as hydrogenated vegetable oils or palm oil are added during the grinding process. These oils help bind the natural peanut oils to the solid peanut particles, ensuring a smooth and stable product that doesn't separate in the jar. Salt and sugar are also added at this stage to enhance the flavor of the peanut butter. Factories use precision dosing systems to measure and add these ingredients in exact proportions, ensuring every batch has the same taste. After grinding, the peanut butter is sent through a mixing stage, where it is further blended in large stainless steel tanks equipped with high-speed agitators. This stage ensures that the stabilizers, salt, and sugar are evenly distributed throughout the peanut butter. These tanks are often heated slightly to keep the peanut butter at the right consistency for mixing. The temperature is carefully controlled, as overheating can alter the flavor or texture of the peanut butter. Once the mixing is complete, the peanut butter undergoes quality control checks. Samples from each batch are tested in an on-site laboratory for flavor, texture, and consistency. Advanced instruments, such as viscometers, are used to measure the viscosity of the peanut butter, ensuring it meets the desired standards. Factories also use particle size analyzers to confirm that the peanut butter's texture is smooth and uniform. These quality checks are critical, as even slight variations can impact the final product's appeal to consumers. The final step in the manufacturing process is packaging. The peanut butter is pumped from the mixing tanks to filling machines, where it is dispensed into jars. These filling machines are capable of handling thousands of jars per hour, ensuring high efficiency. The jars, typically made of food-grade plastic or glass, arrive at the factory pre-cleaned and are sterilized again before filling. The filling nozzles are designed to dispense precise amounts of peanut butter into each jar, ensuring uniform weight and volume. Once the jars are filled, they move to the capping machines, where tamper-proof lids are applied and tightened. After capping, the jars are conveyed to labeling machines, which apply the brand's signature labels, along with lot numbers and expiration dates for traceability. Vision systems inspect each jar to ensure that the labels are correctly applied and that there are no defects in the seals or packaging. The jars are then packed into cardboard boxes using robotic packing systems. These robots are programmed to arrange the jars in specific configurations to optimize space and protect the jars during transportation. The boxes are sealed and stacked onto pallets using automated palletizing systems. Finally, the pallets are wrapped in plastic film for stability and loaded onto trucks or shipping containers for distribution. Throughout the entire production process, automation plays a vital role in maintaining efficiency and consistency. Factories are equipped with programmable logic controllers, PLCs, and supervisory control and data acquisition, SCADA systems, that monitor and control every aspect of production. These systems provide real-time data on parameters such as temperature, pressure, and flow rates, allowing operators to make adjustments as needed. Robotic systems handle many tasks, from sorting and cleaning peanuts to packaging the final product, reducing the need for manual labor and ensuring precision. Hygiene and safety are also top priorities in peanut butter factories. The production areas are constructed with food-grade stainless steel surfaces and epoxy-coated floors that are easy to clean and sanitize. Positive air pressure systems prevent airborne contaminants from entering critical zones, while strict hygiene protocols ensure that employees maintain cleanliness throughout the production process. The entire facility is regularly inspected to comply with international food safety standards, ensuring that every jar of peanut butter is safe for consumption. Peanut butter production is a complex and highly technical process that relies on advanced machinery, precise engineering, and rigorous quality control. From the cleaning and roasting of peanuts to the grinding, mixing, and packaging of the final product, every step is designed to create a spread that is smooth, flavorful, and consistent. Factories operate with remarkable efficiency, producing thousands of jars per day to meet the global demand for this versatile and beloved product. Strawberry jam production is a fascinating and highly engineered process that combines precision machinery with time-tested techniques to create a smooth, fruity spread. At the core of this process are high-quality strawberries, sugar, pectin, and citric acid, all carefully handled and processed to achieve the perfect consistency and flavor. Inside a modern jam factory, every step is optimized for efficiency, consistency, and food safety. The process begins with the selection and delivery of fresh or frozen strawberries. Factories typically source strawberries from local farms or large-scale suppliers. Frozen strawberries are often preferred for large-scale production because they are preserved at peak ripeness, ensuring consistent flavor year-round. The strawberries arrive in bulk containers and are stored in cold rooms or freezers to maintain their quality until processing begins. Before entering the production line, the fruit undergoes a thorough cleaning process. This includes washing the strawberries in large tanks filled with filtered water, where gentle agitation removes dirt, debris, and any residual pesticides. Once cleaned, the strawberries pass through optical sorting machines. These machines use cameras and sensors to identify and remove defective or discolored fruit. Advanced systems can even detect minute imperfections, ensuring that only the highest quality strawberries make it into the jam. After sorting, the strawberries are sent to cutting or mashing machines, depending on the desired jam texture. For chunkier jams, strawberries are coarsely chopped, while for smooth spreads, they are mashed or pureed into a uniform consistency. The fruit then enters large stainless steel cooking kettles or continuous cooking systems. In these vessels, the strawberries are combined with sugar, which not only sweetens the jam, but also acts as a natural preservative. The sugar is added using automated dosing systems that measure precise quantities to ensure consistent flavor. Pectin, a natural thickening agent derived from fruit, is added to help the jam set. Citric acid is also incorporated to balance the sweetness and enhance the fruit's natural flavor. The mixture is slowly heated, with temperatures reaching up to 220 degrees Fahrenheit to activate the pectin and achieve the ideal gel-like consistency. During cooking, the jam undergoes constant agitation to prevent scorching and ensure even heating. Steam-jacketed kettles or vacuum cookers are often used, as they allow for rapid and uniform heating. Modern vacuum systems are particularly advantageous because they enable cooking at lower temperatures, preserving the fresh flavor and bright color of the strawberries. Throughout the cooking process, sensors monitor the temperature, pH levels, and viscosity of the jam, ensuring that the final product meets strict quality standards. Once the jam reaches the desired consistency, it is pumped through a series of filters to remove any seeds or large pieces if a smoother texture is desired. The finished jam is then transferred to filling machines. These machines dispense precise amounts of jam into sterilized glass jars or plastic containers. The jars are immediately sealed with tamper-proof lids to maintain freshness and prevent contamination. After sealing, the jars are passed through pasteurization tunnels, where they are briefly heated to destroy any remaining microorganisms. Finally, the jars are labeled, inspected, and packed into cartons using robotic packaging systems. The entire process is highly automated, ensuring efficiency and consistent quality, from the arrival of fresh strawberries to the delivery of jars to store shelves. This seamless blend of traditional cooking techniques and advanced technology ensures that every jar of strawberry jam is rich in flavor, perfectly textured, and safe for consumers to enjoy. The production of a Mars bar begins with the formulation and creation of its first major internal layer, the nougat. This nougat isn't the brittle kind you might find in traditional nut candies. Rather, it's a whipped, creamy, slightly chewy foundation that gives Mars bars their signature texture. Creating this nougat at industrial scale is a carefully engineered process that blends confectionery science with mass production machinery and strict environmental controls. Before the first batch of nougat is made, however, the ingredients themselves must be prepared and stored according to strict protocols. The base ingredients for the nougat are sugar, glucose syrup, water, fat typically palm or shea oil, dried milk powder, cocoa powder, and whipped egg white or egg albumin. All these materials arrive at the Mars manufacturing facility in bulk, delivered in tankers, tote bags, or sealed sacks. Each delivery is logged, barcoded, and entered into the site's inventory system. But before any ingredient enters production, it must pass Mars' internal quality standards. All dry ingredients, such as sugar and milk powder, are transferred into enclosed silo systems using pneumatic conveyors. These silos are climate-controlled and fitted with HEPA filtration to prevent contamination from dust or ambient air. Each ingredient batch is tagged with a barcode that traces it back to its supplier, production date, and previous storage conditions. For example, sugar may be tested for grain size, purity, and color using laser granulometry and ICUMSA color unit analysis. If it's outside tolerance, it's rejected immediately. Liquid ingredients like glucose syrup and oils are offloaded into jacketed stainless steel storage tanks through filtered, food-grade hoses. These tanks maintain the ingredients at set temperatures to ensure proper viscosity for pumping during production. Glucose syrup, for instance, is kept at around 40 degrees Celsius to remain fluid enough to move through piping without crystallizing. Oils are similarly heated and agitated to prevent separation or solidification. Once all components have been approved and staged, the first step in actual nougat production begins in a dedicated mixing chamber. This space is sealed off from other parts of the factory and maintained at specific humidity and temperature levels to preserve the quality and structure of the aerated product. Airborne particles are filtered through a multi-stage air filtration system, and stainless steel surfaces are sanitized before each production run. Nougat is made in large capacity continuous mixers, automated machines that blend ingredients while precisely managing flow rate, temperature, and mixing speed. In a traditional batch process, workers would mix sugar and glucose syrup with water and cook it to a specific temperature. But in Mars's high-speed factories, this process is carried out on a continuous flow basis, meaning raw ingredients are metered into the cooking system in real time, mixed, cooked, and then aerated in a constant stream. First, sugar, glucose syrup, and water are combined in a jacketed mixing vessel and brought up to temperature using indirect steam heating. The mixture must reach roughly 115 to 120 degrees Celsius, hot enough to dissolve all solids and achieve the correct consistency for whipping, but not so hot that caramelization occurs. Inline refractometers monitor the brix level, sugar concentration, constantly, sending digital signals to a control system that adjusts syrup feed rate or cooking temperature as needed to stay within spec. Once the syrup reaches target temperature and concentration, it's transferred to a cooling chamber. where it's rapidly brought down to around 70 to 80 degrees Celsius using chilled water jackets. This temperature reduction is critical. It stabilizes the syrup mixture and prepares it for aeration with egg whites or albumin, which cannot be added while the base is too hot without denaturing the proteins. Now comes the aeration stage, where the characteristic lightness and chew of the nougat is created. A pre-prepared egg albumin solution is metered into the cooled sugar syrup in a continuous aerator. This machine functions much like a planetary mixer, but at vastly greater speed and scale. Blades spin at extremely high RPMs inside a sealed chamber, while air is injected under pressure. The result is a fluffy, stable foam that has the volume and consistency of whipped marshmallow. The air injected into the aerator is sterile and dry, supplied by an inline compressed air system equipped with microbial filters and dehumidifiers. Pressure, temperature, and air-to-liquid ratio are all controlled automatically via programmable logic controllers, PLCs, which adjust mixing speed and flow rate to maintain uniform aeration. If the density of the nougat mixture falls outside of target specifications, measured by inline densitometers, the system automatically corrects the air or syrup flow or alerts operators to intervene. At this point, cocoa powder and dried milk are added to the base. These ingredients give Mars Bar Nougat its unique color and rich malted taste. They are added using powder feeders that continuously meter the dry materials into the aerated mass as it exits the mixer. This blending occurs in a sealed paddle mixer with gentle, controlled agitation to avoid collapsing the foam structure. The resulting mixture is a warm, chocolatey nougat paste with a light, stable structure and a semi-elastic texture. Now that the nougat base is formed, it must be shaped and cooled. The nougat flows out of the mixer onto a stainless steel conveyor belt, forming a continuous slab about 2 to 3 centimeters thick. This slab passes through a chilling tunnel, where it is gradually cooled from around 60 degrees Celsius to just below ambient temperature. The tunnel uses recirculated cold air, zoned in multiple sections, to cool the nougat evenly without inducing condensation or hardening the outer surface too quickly. As the slab exits the chilling tunnel, it enters a cutting station. Rotary guillotine knives, synchronized with the belt speed, slice the slab crosswise into narrow ribbons, each of which will become the base layer of a Mars bar. These ribbons are then cut lengthwise by inline blades or ultrasonic cutters, creating rectangular nougat centers of uniform size. Every bar section is scanned by vision systems to check for dimensional consistency, length, width, and height, with auto-reject mechanisms removing any pieces that fall outside tolerance. The formed nougat segments are now ready to receive their second major component, the caramel layer. But before caramel is deposited, the nougat sections are spaced and aligned using lane diverters and product guides, ensuring that each bar proceeds uniformly through the next phase of production. The segments then pass into a buffer zone where their temperature is stabilized to prepare for caramel application. Now that the nougat segments are cooled, cut to precise dimensions, and cued in alignment on the conveyor system, the next phase in the Mars chocolate bar manufacturing process begins: the production and deposition of the caramel layer. This caramel is not a generic topping, it's one of the signature components that defines the textural and flavor contrast of a Mars bar. Creating this layer at scale requires a specialized process that integrates continuous cooking, emulsification, temperature control, and precision depositing, all engineered to work seamlessly within the speed and flow of a high-volume confectionery production line. The caramel used in Mars bars is made from a carefully balanced combination of sugar, glucose syrup, sweetened condensed milk or milk solids, and a specific blend of fats and emulsifiers. It's cooked to achieve a particular consistency, not too firm, not too runny, with a creamy chew that holds its shape during wrapping and storage, yet yields easily when bitten into. The production of caramel begins in a dedicated cooking area, separate from the nougat line, but synchronized with it to maintain constant throughput. All ingredients are stored in bulk near the cooking zone. Sugar and milk powders are gravity-fed from silos into high-shear premixes, while glucose syrup and fat are pumped in from temperature-controlled tanks. The emulsifiers, such as mono and diglycerides, are introduced through metering pumps in very small, tightly controlled amounts to help ensure smooth texture and fat-water dispersion. A water phase may also be introduced at the start to aid in initial dissolution and prevent localized overheating. The entire mixture is first blended in a jacketed stainless steel preheating tank, where it's brought to a uniform temperature of around 70 to 80 degrees Celsius. This pre-cooking stage ensures that all ingredients are fully homogenized before entering the main caramel cooker. From here, the caramel mix is pumped continuously into a vacuum caramel cooker, a specialized machine that allows rapid, even heating while removing excess water to control the final solid's content and viscosity. Vacuum caramel cookers work by reducing the internal pressure in the cooking chamber so that water boils off at a lower temperature. This is crucial to avoid burning the sugars or overcooking the milk solids, which could lead to bitter notes or textural instability. Inside the cooker, the mix is heated to between 115 degrees Celsius and 120 degrees Celsius. The target is to achieve a final water content of around 6 to 8%, with a sugar concentration of roughly 80 to 85 brix. Inline refractometers monitor this constantly, and the cooker adjusts residence time or heating level as needed to meet the spec. Once cooked, the caramel exits the cooker as a thick, glossy liquid with a rich golden brown hue. But before it can be applied to the nougat, it must be slightly cooled and tempered to a very specific range, typically between 45 degrees Celsius and 55 degrees Celsius. This cooling step stabilizes the caramel structure, allowing it to flow evenly during deposition without dripping or bleeding into the nougat layer. Cooling is performed in a jacketed holding tank equipped with slow-speed agitators that prevent crusting and keep the mixture homogeneous. With the caramel at the correct temperature, it's piped toward the depositing station. Here, the aligned nougat segments are conveyed under a continuous curtain-style depositor or a series of timed nozzles. Each piece receives a uniform layer of caramel, typically around 5 to 6 millimeters thick, depending on the final product specification. The depositor is precisely synchronized with the line speed, often using servo motors and optical sensors, so that each caramel stream lands squarely on the nougat block without overflow or excess. In higher speed lines, a pre-formed caramel sheet may be used instead. In this method, caramel is spread onto a separate cooling belt, allowed to set into a thin slab, and then laminated onto the nougat in one continuous motion using compression rollers. This technique allows better layer thickness control at very high production speeds and ensures cleaner edges for slicing. Once the caramel is applied, the dual layer bar now enters another cooling tunnel, usually a multi-zone refrigerated belt system that brings the caramel from 50 degrees Celsius down to just under 20 degrees Celsius. This cooling step must be gradual and controlled. Too rapid, and the caramel may contract unevenly, leading to separation from the nougat. Too slow, and it may remain sticky, interfering with the next step. Chocolate enrobing. During cooling, the layered bar is gently compressed by a roller to ensure adhesion between nougat and caramel. Then, it's passed through edge trimmers, which shave off the sides of the slab to produce perfectly square bars with clean, vertical sides. These trimmed edges are not wasted. They are collected via vacuum conveyors and reprocessed, either remelted or reformed, depending on factory protocol. The bar, now comprised of a cooled nougat base and a bonded caramel layer, is next cut into individual pieces using high-speed guillotine cutters. These are precision machines equipped with hardened stainless steel blades or ultrasonic cutting systems that minimize drag and preserve edge integrity. Each piece is exactly the length and width of a finished Mars bar, around 10 centimeters long and weighing roughly 51 to 57 grams, depending on the market. As the bars are cut, they are spaced out evenly using puck conveyors or lane dividers, aligning them perfectly for entry into the chocolate enrobing section. The temperature, moisture, and dimensional uniformity of each bar are verified by inline sensors and vision systems. Bars that are cracked, too short, or unevenly shaped are automatically diverted off the line for manual inspection or rework. At this stage, we transition into the enrobing process, the iconic step where each bar is coated in a smooth layer of Mars proprietary milk chocolate blend. This chocolate is stored in large tempering tanks, located just prior to the enrober. These tanks keep the chocolate at the ideal crystallization state, ensuring a glossy finish and firm snap after cooling. The chocolate used in Mars bars is a blend of cocoa liquor, cocoa butter, sugar, and milk solids, with added emulsifiers like soy lecithin to enhance flow properties. The tempered chocolate is pumped into the enrober, which is essentially a tunnel lined with a bottoming section to coat the base of each bar, and a curtain section to drape chocolate over the top and sides. Each Mars bar passes first over a shallow pool of chocolate to coat its underside, then directly beneath a flowing curtain that envelops the rest of the bar. A gentle stream of warm air is directed across the top to remove excess and create a rippled surface texture, a distinctive feature of the Mars bar. After enrobing, the bars are conveyed into the cooling tunnel, an extended refrigerated belt system approximately 20 to 30 meters in length. Inside, the environment is segmented into zones that gradually lower the temperature of the bars from around 32 degrees Celsius to 10 degrees Celsius. This staged cooling helps the cocoa butter in the chocolate crystallize properly, locking in the sheen and texture while avoiding fat bloom or streaks. Throughout this tunnel, air humidity is tightly controlled, generally under 50%, to prevent condensation on the chocolate. Dew point sensors and fans work in tandem with the refrigeration units to maintain a stable microclimate. The bars spend 5 to 8 minutes in this tunnel before emerging with fully set coatings, ready for packaging. As the cooled and finished bars exit the tunnel, they're fed into accumulation conveyors and grouped for wrapping. Each bar passes through a flow wrapping machine where printed film is unwound, formed into a sleeve, and sealed around the product. The wrapper is then crimp sealed on both ends and trimmed. These wrapping machines can process hundreds of bars per minute, and each wrapped bar is weighed and scanned before being discharged onto final packing belts. At this point, the product is visually indistinguishable from the Mars bar found on store shelves, but the process is still not finished. The next stage involves secondary packaging, grouping bars into boxes, cartons, and shipping trays, and preparing them for distribution. As the fully formed, enrobed, and cooled Mars bars make their way off the production line, they enter the final stages of the factory process, beginning with high-speed wrapping and continuing through automated boxing, palletization, storage, and outbound logistics. These downstream systems are critical not just for protection and presentation of the product, but also for ensuring traceability, quality retention, and supply chain synchronization. While the visible production, the mixing, cooking, cutting, and coating is complete, the final packaging and handling stages are no less intricate, built on robotics, data systems, and industrial automation designed to manage millions of units every day. The first stop is the wrapping station. Here, each Mars bar moves along the conveyor belt in single file toward the flow wrapping machine. This machine feeds a continuous roll of printed film into a series of folding arms and sealing jaws. As each bar enters, the film wraps around it in a tight, tubular sleeve, and heated crimp jaws at either end form the back seal and the end seals simultaneously. The temperature of these jaws is maintained within a few degrees of the sealing material's activation point to ensure strong, clean closures without melting or burning the film. Mars uses multi-layered packaging films that are designed not only to provide barrier protection against oxygen and moisture, but also to deliver the tactile feel and gloss that customers expect from premium chocolate packaging. The inner layer is typically a heat-sealable polymer. The middle layer may include aluminum or metallized PET for barrier properties. And the outer layer is printed with brand artwork and product information. The printed designs are registered with high-precision sensors, so every bar's logo aligns perfectly. Any misregistered wrapper is automatically detected and rejected by an optical scanner system. Once sealed, the wrapped bar passes over a check weigher, an in-motion scale that ensures the final packaged weight is within tolerance. If a bar is over or underweight, even by a gram, it's automatically diverted. Next, each unit is passed under a metal detector, which checks for any possible foreign objects that could have entered the bar during earlier processing stages. These systems are highly sensitive and calibrated daily with test pieces. Some plants also employ X-ray machines that detect not just metal, but dense, non-metallic contaminants, such as glass or stone. Bars that pass all inspections continue down the conveyor toward the cartoning line. Depending on the intended retail format, bars may be grouped into multi-packs, retail-ready trays, or shipping cartons. Robotic arms, or high-speed diverters, organize the flow of individual bars into stacks, 4, 6, 10, or 12 bars wide, and gently push them into pre-folded cardboard sleeves or boxes. These secondary packages are then sealed using hot melt glue or tuck-in flaps, depending on market requirements. Each package receives a printed label with batch number, timestamp, factory ID, and possibly a QR code for inventory tracking. From here, boxed products are routed to the palletizing station. Robotic palletizers pick up full cases using vacuum grippers or mechanical arms and stack them on wooden or plastic pallets in precise formations. Each layer is arranged to optimize space, balance, and load stability. Between layers, some systems add cardboard slips or corner protectors for reinforcement. Once the pallet reaches its programmed height, typically 1.6 to 1.8 meters, it's wrapped in stretch film by an automatic wrapper, which rotates the pallet while dispensing the film under tension to secure the load. The wrapped pallets are then fitted with pallet labels that include the SKU, total unit count, gross weight, destination code, and a unique identifier that ties back to the factory's internal tracking system. These labels are printed by thermal printers and verified by barcode scanners before the pallets are cleared to enter the finished goods warehouse. Before we go further, it's important to recognize the role of Mars factory control systems in managing this entire post-production phase. All equipment is integrated into a centralized manufacturing execution system, MES, that tracks every product in real time. Each bar, box, and pallet carries data, embedded in barcodes or RFID tags, about when it was made, on which line, using which ingredients, and under what conditions. This traceability is a cornerstone of food safety compliance and internal quality assurance. The finished goods warehouse is where the newly palletized bars await shipment. This warehouse is fully climate controlled to maintain optimal temperature and humidity for chocolate storage. Temperature is held at 18 to 20 degrees Celsius with relative humidity below 55% to prevent bloom, melting, or texture changes. Air circulation systems keep temperature consistent throughout the space, while insulation and vapor barriers prevent external fluctuations from impacting internal conditions. Inventory in the warehouse is managed using automated guided vehicles, AGVs, or forklifts equipped with real-time location systems. When pallets are stored, they're scanned into the warehouse management system and placed according to distribution priority. High turnover products are stored closer to the shipping bays, while seasonal or export variants may be stored deeper in the racking system. The storage time for any batch is typically less than a week, as Mars factories operate on just-in-time logistics, pushing product out daily to meet distributor orders. When shipments are requested, the warehouse team receives a digital pick list. AGVs or operators retrieve the designated pallets, verify them via handheld scanners, and stage them at the outbound docks. Before loading, each shipment is inspected to ensure it matches the order specification, is within temperature tolerance, and has intact pallet wrapping. Refrigerated or climate-controlled trucks are often used for long-distance shipments or deliveries to regions with high ambient temperatures. Loading is done using dock levelers and roller systems to ensure smooth movement and prevent tipping. During transit, temperature loggers accompany the shipments, recording data at set intervals. These loggers are checked upon delivery, and if any deviation from the acceptable range is detected, the shipment may be flagged for inspection or rejection. Mars also monitors customer feedback, market audits, and in-store quality surveys. Samples of each production lot are retained in climate-controlled storage at the factory for shelf life testing. These retained samples are periodically tested for appearance, taste, texture, and microbiological stability over the course of months, ensuring that every production protocol performs as expected long after the product has left the plant. Parallel to all of this is a dedicated quality control laboratory. Here, daily production samples are subjected to physical and chemical analysis. Moisture content, fat content, sugar crystallinity, pH, and emulsion stability are checked using instruments like Carl Fisher titrators, differential scanning calorimeters, and viscometers. Sensory panels trained in Mars' specific flavor and texture profiles evaluate samples for aroma, mouthfeel, and aftertaste. Auditors regularly conduct surprise inspections, testing product against regulatory standards in every region the factory exports to. Some facilities even run accelerated aging chambers, simulating 6 months of shelf life in a few weeks using controlled temperature and humidity cycling. This allows the company to predict how new packaging or ingredient changes may impact long-term stability before releasing them to the market. Within the final layers of Mars' chocolate bar manufacturing process lies an often unseen yet deeply critical infrastructure dedicated to innovation, iteration, and global standardization. While the production lines are optimized for high-speed consistency, behind the scenes, the company operates pilot plants and R&D laboratories, where new formulations, production methods, and equipment calibrations are continuously tested, refined, and validated before they're deployed across global facilities. Every Mars chocolate bar, regardless of where it is produced, in the United States, the United Kingdom, or other licensed manufacturing hubs, must adhere to an extremely narrow window of variation. This means the bars must look, taste, feel, and behave identically, despite being produced in plants thousands of kilometers apart. Achieving this demands extensive process documentation, real-time data comparison, and coordinated updates to recipes and equipment settings across all sites. Pilot plants, often located adjacent to main production facilities, house miniature versions of the full-scale equipment, scaled-down mixers, depositors, tempering tanks, and enrobers, used not just for prototyping new flavors or bar formats, but also for stress testing ingredient substitutions, adjusting for new cocoa sources, or modifying emulsifier levels in response to regional ingredient availability or regulation. A new Mars bar variant, such as one with an added layer of cookie or a salted caramel flavor, may go through dozens of test batches before scaling. Each trial is evaluated not just for consumer preference, but for how it performs on actual equipment. Does the caramel spread at the correct rate on moving belts? Does it maintain form through the cooling tunnel? Does the chocolate enrobe correctly without altering crystallization time? These questions are answered with data from test runs that are digitally logged and used to generate predictive models before any large-scale production begins. Digital twins, virtual simulations of real production environments, are increasingly being used in these trials. These tools model fluid dynamics, thermal behavior, and mechanical stress on ingredients during cooking, cooling, and transport. They allow engineers to simulate a dozen line changes without touching a single piece of physical equipment, drastically accelerating the pace of safe innovation. Once a new process is approved, Mars Global Standardization Team prepares comprehensive change packs, which include updated process parameters, safety protocols, ingredient specs, equipment calibration charts, and software updates. These packs are then distributed to all regional manufacturing hubs, often followed by remote training sessions or on-site visits to ensure implementation is seamless. This global coordination ensures that whether you open a Mars bar in Chicago, Sydney, or Madrid, the experience is identical, down to the snap of the chocolate, the elasticity of the caramel, and the melt rate of the nougat. The production of Starbucks products, particularly its packaged coffee offerings that end up in grocery stores, retail outlets, and international supply chains, begins long before a single bean is roasted. The entire process is built on one foundational element: green coffee sourcing. Starbucks, known for its commitment to quality and consistency, manages one of the most tightly controlled and globalized green coffee sourcing operations in the food and beverage industry. This first phase, the pre-roasting segment, is where the company sets the tone for every cup of coffee or bottled product it will eventually serve. And it's here we begin our highly detailed step-by-step journey. The green coffee sourcing process starts at origin in the tropical coffee-growing regions that straddle the equator, primarily Latin America, East Africa, and Southeast Asia. Starbucks primarily uses Arabica beans due to their more nuanced flavor profiles compared to the hardier but less complex Robusta variety. Within the Arabica family, beans are selected based on elevation, soil composition, rainfall, and harvest timing. Starbucks maintains long-standing relationships with coffee growers, cooperatives, and export mills in countries like Colombia, Ethiopia, Guatemala, Indonesia, Brazil, and Rwanda. But it's not as simple as ordering beans in bulk and having them shipped. Starbucks uses a proprietary set of sourcing standards known as Coffee and Farmer Equity Practices. These standards are not only a requirement for suppliers to be eligible, but also a multi-layered auditing framework. CAFE practices address 4 critical areas: product quality, social responsibility, environmental leadership, and economic transparency. Every farm or co-op that sells beans to Starbucks must pass rigorous inspections in these categories, many of which are carried out by third-party auditors trained in agricultural and labor practices. Once a farm or producer is approved under CAFE practices, the beans are harvested, typically by hand. Hand-picking ensures that only ripe coffee cherries are selected, an essential factor in achieving flavor consistency in the final roast. These cherries are then processed at or near the farm using either the washed method. The washed method involves removing the pulp and fermenting the beans to eliminate the mucilage before drying, producing a cleaner, brighter flavor. The natural method dries the entire cherry and imparts a fruitier, heavier profile. The method used depends on the country, the farmer's infrastructure, and the target flavor profile desired by Starbucks blending teams. Once processed, the green beans are dried to a specific moisture content, usually between 10% and 12%, and stored in parchment until they are ready for export. Before leaving the origin country, the beans undergo a final hulling process to remove the parchment layer. At this stage, Starbucks' quality assurance teams at origin perform multiple assessments. These include physical evaluations and cupping, an industry-standard tasting method. Starbucks QA cuppers evaluate the green coffee on attributes like acidity, body, balance, sweetness, and aftertaste. Only those lots that meet Starbucks' sensory and structural requirements are approved for shipment. Approved beans are then packed into multi-layered jute bags with protective liners or into GrainPro plastic bags that guard against moisture and pests during transit. Each bag is tagged with a traceable barcode or lot number, which connects it to a digital database. This data includes not just the country and region of origin, but the exact farm or cooperative, harvest date, processing method, and quality score. This traceability is critical, not just for transparency and accountability, but also for quality replication year after year. Now begins the logistics phase. Starbucks contracts with specialized freight companies that understand the requirements of green coffee shipping. These beans are incredibly sensitive to temperature and humidity, even in raw form. A single exposure to high heat or excess moisture during transit can cause mold growth or flavor degradation. The beans are typically transported in temperature-stabilized shipping containers. If traveling by sea, the containers are outfitted with humidity control packs and dehumidifying systems. If air freight is used, the bags are carefully palletized, shrink-wrapped, and tagged with sensors that monitor environmental conditions throughout the journey. Upon arrival at one of Starbucks' roasting and manufacturing facilities, such as those located in York, Pennsylvania, Augusta, Georgia, Sandy Run, South Carolina, or Amsterdam, Netherlands, the green beans are unloaded, inspected, and entered into the factory's inventory management system. Before any production begins, each new shipment undergoes additional quality control. Samples from each bag or container are pulled and brought into the sensory lab. There, certified coffee graders perform cupping again, this time to ensure no quality loss occurred in transit. Moisture content, bean uniformity, and fragrance are retested. Beans that pass, these checks are tagged and routed to storage silos within the facility. These silos are food-grade, airtight steel vessels with internal climate regulation. Beans are stored based on variety, region, and intended blend. For example, Latin American beans destined for Starbucks blonde roast will be siloed separately from Ethiopian beans used in Starbucks Reserve offerings. Every silo is equipped with moisture sensors, thermometers, and pneumatic conveyor links, allowing operators to pull precise quantities for each roast batch according to master recipes. Before roasting can begin, beans are weighed into batches according to a specific ratio, depending on the blend being produced. Starbucks maintains an extensive library of proprietary blends, each with precise formulas. Some are single origin, where only one type of bean is used, while others, like Pike Place Roast or Espresso Roast, combine beans from multiple origins. Each blend is documented in the factory's recipe management software, which automatically calculates the needed amount of each component down to the gram and interfaces with weigh-scale systems to ensure accuracy. At this point, the beans are ready for roasting, but that process is highly intricate and deserves its own full analysis. Starbucks does not simply roast coffee by applying heat until the beans turn brown. The next step involves drum roasters, roast curves, heat profiling, airflow modulation, and real-time chemical transformation monitoring that will take the green coffee and convert it into the rich, aromatic, deeply flavored roasted beans that Starbucks is known for worldwide. With the green coffee beans now housed in precision-monitored silos and organized by blend formulation, the next phase of Starbucks' industrial production process transitions into what is often regarded as the heart of the entire operation: roasting. This stage is where the true transformation begins. The raw, pale green beans, earthy, grassy, and flavorless in their original state, are subjected to meticulously calibrated heat treatments that unlock their signature color, aroma, body, and complexity. Starbucks takes this phase extremely seriously, investing in proprietary roast profiles, customized equipment, and a multi-layered monitoring system to ensure that every batch matches the company's highly specific taste standards. The roasting process begins when a batch of green beans is called for from the storage silos. These silos are directly connected to the roasting equipment via stainless steel pneumatic transfer tubes. When an operator initiates a roast cycle, a preset quantity of beans, anywhere from 100 to 600 kilograms, depending on the size of the roaster, is discharged from the silo and transported through vacuum-sealed lines to the roaster's holding hopper. Here, the beans are pre-weighed on industrial platform scales connected to the plant's central production database, ensuring the exact quantity is delivered as dictated by the roast formula for that specific product, whether it's French roast, Pike Place, Sumatra, or espresso. Starbucks uses drum roasters for most of its large-scale production. These roasters consist of a rotating steel drum with an internal blade assembly that keeps the beans in constant motion. This ensures even exposure to heat as the drum is gradually raised to operating temperature, typically ranging between 190 degrees Celsius and 240 degrees Celsius, depending on the roast level. Lighter roasts, such as blonde roast, are roasted to lower final temperatures, while darker roasts, like French or Italian, require longer exposure and higher terminal heat. The roasting process follows a specific curve known as a roast profile. This is a data-driven graph that plots time against temperature, representing how heat is applied across the roast cycle. Starbucks profiles are proprietary and tightly controlled, with each product requiring a unique curve to deliver its intended flavor profile. These curves are not linear. They involve temperature ramps, plateaus, and even controlled dips. The initial drying phase lasts for several minutes, during which moisture is driven out of the bean. This is followed by the Maillard reaction phase, where sugars and amino acids begin to react, producing the rich brown coloration and the first wave of complex aromas. The most critical moment in roasting is known as first crack. This is when internal pressure in the bean causes it to physically crack open, producing an audible popping sound, much like popcorn. This marks a key transformation in bean chemistry. Starbucks roast operators listen for this moment, using audio sensors and thermal feedback to identify it precisely. Lighter roasts may be completed shortly after first crack, while medium and dark roasts continue through the development phase, where oils begin to emerge on the surface and flavor compounds deepen. Throughout this process, the roaster's control panel displays live data for bean temperature, exhaust temperature, airflow rate, and drum speed. The system is equipped with PID controllers and data logging software that feed into the factory's centralized SCADA system. Every roast is archived digitally, allowing Starbucks to recreate identical roast profiles across facilities on different continents, ensuring global consistency. Once the beans reach their designated roast level, they are immediately discharged from the drum into a cooling tray located below the roaster. This tray contains a rotating arm assembly that stirs the beans, while powerful fans blow ambient or chilled air upward from perforated grates below. Rapid cooling is essential to halt the roasting process and lock in the intended flavor and roast depth. If the beans are allowed to remain hot too long, they may bake, resulting in a flat, dull cup profile. The entire roasting to cooling process for a batch of coffee typically takes between 10 and 15 minutes, depending on the desired roast level and bean origin. Once cooled, the roasted beans are conveyed into degassing hoppers, stainless steel holding vessels, where the coffee rests for a short period, usually 12 to 24 hours. This rest period is necessary to allow CO2, a natural byproduct of roasting, to escape. If roasted beans are packaged too soon, the trapped gas can compromise packaging seals or even cause bags to inflate and rupture. However, some CO2 is desirable, especially for brewing freshness, so the timing of degassing must be carefully controlled. During this resting period, samples of each roast batch are collected and sent to the on-site sensory lab. Here, trained cupping teams evaluate the beans using controlled brewing and tasting protocols. They assess key attributes like aroma, acidity, balance, mouthfeel, finish, and overall quality compared to Starbucks' master profile for that roast. Cupping is performed blind and in duplicate to eliminate bias and ensure accuracy. If a batch falls outside of the acceptable range, it may be blended with other batches to correct the profile, used for internal consumption, or in rare cases, discarded. Once a roast batch passes quality inspection, it is routed towards the grinding and packaging area. Some products, like whole bean offerings, will skip the grinding stage entirely, while others destined for ground coffee bags or capsules will be milled using precision grinders. These machines are fitted with hardened steel burrs or rollers that crush the beans to an exact particle size distribution. Starbucks defines specific grind profiles depending on brewing method. For example, drip coffee grind is coarser than espresso grind, and French press is coarser still. Grinding is a highly sensitive operation. During the process, friction from the burrs generates heat, which can degrade volatile aromatics if not carefully controlled. To counter this, industrial grinders are equipped with chilled air systems and thermocouple sensors that regulate burr temperature and prevent overheating. In many facilities, grinding is conducted in a temperature-controlled room or during cooler hours of the day to preserve freshness. As soon as the coffee is ground, it moves to packaging, often through vacuum-sealed transfer tubes that prevent oxidation. The packaging stage is designed to preserve flavor and aroma while ensuring shelf stability. Starbucks uses multi-layer barrier films for its ground coffee products. These films include aluminum or metallized polyester layers that block oxygen and moisture. Many packages are fitted with one-way degassing valves that allow CO2 to escape without letting oxygen in, protecting the coffee's integrity while preventing package ballooning. Packaging machinery includes vertical form fill seal systems for smaller bags and horizontal form fill seal machines for pillow packs or multi-packs. Each package is filled to a specific weight, sealed, and coded with production data, including roast date, location, shift, and lot number. High-speed check weighers and vision systems verify fill accuracy, seal integrity, and barcode clarity. Any package that fails inspection is automatically diverted off the line for rework. After packaging, the coffee products are grouped into cases and transferred to automated case packers and palletizers. Pallets are wrapped and labeled, then stored in temperature-controlled warehouses before shipping. These final steps, inventory control, cold chain monitoring, and outbound logistics, are critical to ensure the roasted Starbucks product reaches distribution centers and retail shelves around the world in optimal condition. With the coffee beans now expertly roasted, cooled, rested, and either packaged whole or ground and sealed, Starbucks' industrial production extends into another critical manufacturing domain, the preparation of its ready-to-drink beverages. These include bottled frappuccinos, chilled espresso drinks, cold brews, and dairy-based coffee blends. These products are not created in the same facilities that handle roasting and bagging. Instead, Starbucks partners with specialized beverage manufacturing facilities. Many cooperated with industry leaders like PepsiCo through the North American Coffee Partnership to manage this high-volume cold fill production. This stage involves liquid formulation, blending, thermal processing, homogenization, and sterile packaging under rigid food safety standards. The process begins with the formulation of the beverage base. For a bottled frappuccino, for example, This includes several core ingredients: brewed coffee extract, filtered water, sugar or corn syrup, dairy or dairy alternatives, stabilizers, and natural or artificial flavorings like vanilla, caramel, or mocha. Each component must be handled separately with precision before it's brought into the blending system. Coffee extract is typically delivered in concentrated form, produced by either brewing Starbucks beans at scale or using advanced extraction methods like cold concentrate percolation or high-pressure brewing. This extract arrives in refrigerated, food-grade totes or tanker trucks, depending on batch size. Upon arrival, it is sampled, analyzed for strength, and approved by the on-site quality control team before entering the liquid ingredient holding tanks. Simultaneously, dairy components such as milk and cream are received through chilled pipelines or aseptic bag-in-box systems. Dairy intake systems in Starbucks RTD plants are equipped with plate heat exchangers to quickly chill and store milk at temperatures below 4 degrees Celsius to maintain freshness and prevent bacterial growth. If using shelf-stable milk or UHT-treated dairy, the plant will still hold the product under cold storage until use. For plant-based SKUs, oat milk, almond milk, or soy milk are stored and handled in similar systems, albeit through dedicated lines to avoid allergen cross-contamination. Sweeteners and stabilizers such as sugar, corn syrup solids, carrageenan, cellulose gum, and pectin are weighed and pre-mixed in separate tanks. Starbucks beverages are engineered not just for taste, but for texture, mouthfeel, and visual consistency, especially in cream-based products like bottled mochas and vanilla frappuccinos. The stabilizers help suspend coffee solids, prevent dairy separation, and ensure the beverage maintains a smooth, homogeneous appearance on shelf, even after weeks or months in cold chain storage. All of these components, coffee extract, dairy or alternative milk, sweeteners, water, and flavor compounds, are brought together in the blending system. This usually consists of large stainless steel jacketed mixing tanks ranging from 1,000 to 5,000 liters. Each tank is equipped with an internal agitator, a bottom-mounted high-shear mixer, and in some cases, inline emulsifiers or homogenizers to ensure all elements are fully integrated. Tanks are fitted with load cells and flow meters, enabling automated dosing of each ingredient according to pre-programmed batch recipes. The blending system is monitored via a central control unit, typically a PLC-connected touchscreen interface that displays real-time values for temperature, mixing speed, pH, and ingredient flow. Operators can monitor the tank's temperature curve, the shear level during mixing, and the dwell time of each phase. In a typical Starbucks RTD batch, the blending cycle lasts between 30 and 60 minutes. During this time, inline sensors monitor turbidity, Brix, and viscosity. Samples are taken periodically to verify pH, flavor intensity, and microbial load before the batch is cleared for downstream processing. Once the beverage blend is complete and validated, the next stage is thermal processing. Most Starbucks RTD beverages are pasteurized using high-temperature, short-time systems, which allow for rapid heat treatment without compromising taste or texture. In HTST, the product is pumped through a heat exchanger that raises the liquid temperature to 85 degrees Celsius to 95 degrees Celsius for 15 to 30 seconds, then rapidly cools it to filling temperature, usually between 4 degrees Celsius and 10 degrees Celsius for cold fill lines, or slightly higher for hot fill bottles. This process effectively destroys any pathogenic microbes while preserving the coffee's aroma and flavor. Some facilities use ultra-high temperature processing for shelf-stable lines, allowing the product to remain unrefrigerated until opened. In UHT, the beverage is flash heated to temperatures up to 140 degrees Celsius for just a few seconds, then cooled quickly before packaging. The decision between HTST and UHT depends on the specific product's shelf life goals. packaging type, and distribution model. Immediately following thermal processing, the beverage passes through an inline homogenizer. This device applies intense pressure, often in excess of 2000 psi, to the liquid through a narrow valve, breaking down fat globules and suspended solids into microparticles. This step is critical for emulsion stability, preventing the cream from separating from the coffee or the flavor oils from rising to the surface. Homogenization also improves mouthfeel, making the beverage taste creamier and smoother. From here, the liquid is conveyed to the filling system. Starbucks RTD products are filled into a variety of package types: PET bottles, glass bottles, aluminum cans, and aseptic cartons. Each format requires its own dedicated filling and sealing system. For bottled frappuccinos, a cold fill rotary filler is typically used. This high-speed machine feeds sterilized bottles onto a rotating platform, where they are filled by gravity or volumetric fillers to exact fill levels. Immediately afterward, caps are applied, using steam-assisted capping heads to ensure a vacuum-tight seal and tamper resistance. Cans and cartons are filled on their respective lines, cartons often using form-fill-seal machines that shape the container, fill it, and seal the top in one continuous motion. All packages pass through automated detection systems that verify fill levels using weight sensors, check cap placement with vision systems, and scan barcodes to confirm packaging accuracy. Reject mechanisms immediately remove any container that fails these criteria. The filled beverages are then passed through a secondary cooling tunnel or refrigerated spiral conveyor that ensures they reach their final holding temperature before entering the packaging area. Depending on the product, this may be as low as 2 degrees Celsius, especially for refrigerated drinks destined for grocery and convenience store cold vaults. Once cooled, the individual containers are collected into multi-packs, shrink-wrapped, and placed into branded cartons. These cartons are then palletized by robotic arms and wrapped with plastic film. Each pallet is labeled with a unique identifier, linking it to the specific batch number, production date, filler line, and formulation ID. All of this information is uploaded into the factory's ERP system, providing full traceability from bean to bottle. Before any shipment is cleared, final product samples are pulled from each pallet for comprehensive testing. These include microbial testing, shelf stability stress tests, and sensory evaluations by trained panels. Only after all tests are passed are pallets released into refrigerated distribution channels for delivery to retail partners, Starbucks cafes, or direct-to-consumer platforms. From formulation and blending to pasteurization, homogenization, and ultra-clean packaging, this RTD production phase represents one of the most technologically advanced parts of Starbucks' global supply chain. It's where liquid meets logistics, combining industrial food science with tight controls over quality, taste, and branding. Every chilled bottle or can represents thousands of interconnected variables managed with absolute precision to deliver a consistent, enjoyable Starbucks experience anywhere in the world. With Starbucks ready-to-drink beverages now filled, sealed, chilled, and palletized, the focus shifts to the final, but no less complex, elements of factory operations. Sustainability integration, byproduct management, batch auditing, and outbound logistics. While the product may appear finished at this stage, the systems behind its release are still active, ensuring every bottle or can shipped reflects the brand's uncompromising quality, environmental responsibility, and traceability. One major component of this final phase is waste stream management. Every Starbucks beverage production facility is designed to minimize waste and make use of byproducts wherever possible. Coffee grounds remaining from extract production are collected and either sent to composting facilities, transformed into animal feed, or, in more advanced plants, used as biomass fuel to generate energy. Spent dairy materials or cleaning water are filtered and treated through on-site wastewater management systems, often returning grey water to municipal treatment plants within strict pH and chemical parameters. Packaging waste, including edge trims from shrink wrap film, carton misprints, and PET bottle scrap, is separated and sent to in-factory compactors and balers. These bales are transported to certified recyclers for reprocessing. Starbucks has implemented programs at several manufacturing locations that convert unrecyclable soft plastics into composite shipping pallets or building materials, helping close the loop on production materials. In parallel with waste management, quality auditing continues even after packaging. Randomly selected finished products are pulled from every batch and routed to a dedicated quality assurance lab within the facility. There, they undergo another round of microbiological testing, sensory analysis, packaging integrity checks, and accelerated aging simulations. These simulations might involve storing the product at elevated temperatures for several days or weeks to mimic what could happen during prolonged distribution delays. Any deviation in flavor, appearance, or microbial safety can trigger a hold on the entire batch while root causes are investigated. All data generated, from roast date to filler head temperature, from pallet wrap tension to microbial test results, is logged in the facility's centralized manufacturing execution system. This digital record ensures that any shipment can be traced back through every step of the factory process. If a product recall is ever initiated, these logs allow immediate identification of affected units by date, location, and even by hour of production. When cleared, the finished pallets are scheduled for outbound logistics. Route planning software, inventory analytics, and order data from Starbucks' retail and grocery distribution teams are combined to determine where each batch will go. Products destined for grocery stores enter the cold chain system, transported in refrigerated trucks with temperature logs monitored in real time. Others, such as shelf-stable offerings, are routed to ambient storage hubs or export terminals for international shipping. To craft Starburst, factories begin with a foundation of raw materials, with the primary ingredients being sugar, corn syrup, hydrogenated palm kernel oil, fruit juice concentrates, citric acid, and natural and artificial flavors. Food-grade colorants such as red 40, yellow 5, and blue 1 give the candy its vibrant, recognizable hues. Sugar, the dominant ingredient, is typically sourced from sugar beets or sugar cane, refined to a fine, white granulated form. Corn syrup, essential for achieving the chewy consistency, is extracted from dent corn and then enzymatically converted into glucose-heavy syrup. This syrup not only sweetens, but also inhibits crystallization, allowing for the distinctive, flexible Starburst chew. Fruit juice concentrates are selected based on seasonal availability and flavor profiles, often involving apple, cherry, orange, strawberry, lemon, and other citrus bases. Each concentrate is filtered and reduced under vacuum conditions to intensify the flavor while removing excess water. Meanwhile, citric acid, either derived from citrus fruits or biosynthesized using Aspergillus niger fermentation, is added to sharpen the tart notes and stabilize the pH level. Palm kernel oil, after undergoing hydrogenation to solidify its structure, contributes to the smooth mouthfeel, acting as a lubricant and textural agent within the candy matrix. All of these ingredients are delivered to the factory in bulk, sugar and corn syrup via silo systems and tanker trucks, oils in heated storage tanks, and flavoring agents in sealed food-grade containers to maintain freshness and prevent contamination. Once inside the facility, the first major step in the Starburst making process is ingredient weighing and batching. Massive computerized batching systems measure exact quantities of each component using load cells and automated valve controls. Sugar and corn syrup are combined in stainless steel jacketed mixing tanks where they are preheated to around 115 degrees Celsius. This begins the process of dissolving the sugar crystals into a homogeneous syrup base. Agitators inside the tanks ensure uniformity and prevent scorching. The heated syrup is then transferred to a vacuum cooker. In the vacuum cooking chamber, the syrup is exposed to reduced atmospheric pressure, allowing water to evaporate at a lower temperature. This technique is critical in candy making, as it prevents the sugar from caramelizing or breaking down under intense heat. As moisture is removed, the syrup thickens into a viscous mass with a specific Brix value, typically between 85 and 90% solids content, ensuring it will solidify into a chewy form once cooled. The exact cooking time and temperature are closely monitored via sensors and control systems linked to the plant's supervisory control and data acquisition platform, or SCADA. After cooking, the thickened candy mass is transferred through heated conduits into a mixing chamber known as a color and flavor cooker, or kneader. Here, hydrogenated palm kernel oil is added to help emulsify the mixture and control the final texture. Food-safe mixing blades, often paddle style or Z-blade types, churn the mass at controlled speeds. This is also the point where colorants, acids, and flavor concentrates are injected. High-precision peristaltic pumps ensure accurate dosing of color and flavor to maintain batch consistency, and the mixer is divided into multiple compartments if producing more than one flavor at a time. For instance, strawberry might be mixed in one chamber, lemon in another, and cherry in a third. Each batch customized with different concentrations of fruit essence and specific pH levels for optimal taste balance. Once the flavor-specific masses are ready, they must be cooled to a workable temperature, typically around 60 degrees Celsius, before shaping. Cooling belts equipped with air curtains and stainless steel rollers gently lower the temperature without causing hardening or premature setting. From here, the candy mass is directed into the forming line, a highly orchestrated system of extrusion, cutting, and wrapping. Extrusion is the next key phase. Using positive displacement gear pumps, or auger-driven extruders, the warm candy mass is pushed through stainless steel nozzles with rectangular cross-sections. This creates long, continuous ropes of candy with a consistent width and height, matching the final Starburst dimensions. Servo motors carefully control the extrusion speed to synchronize with the downstream cutting process. If multiple colors or flavors are being co-extruded, special twin-screw extruders equipped with internal baffles can combine two masses into a single, dual-colored strand, which adds visual interest and flavor complexity. The ropes move onto a conveyor equipped with cooled rollers to maintain their shape. A high-speed guillotine cutter, controlled by an optical sensor system, slices the rope into individual blocks with precise timing. The cutting knives are made from food-grade stainless steel and are lubricated with a microfine spray of food-grade oil to prevent sticking. Each candy piece is now in its iconic rectangular shape, ready for wrapping. Wrapping Starburst is a marvel of mechanical ingenuity. Each piece must be individually wrapped in waxed paper to preserve freshness and prevent sticking. Automatic folding and wrapping machines, operating at speeds of up to 800 pieces per minute, perform this delicate operation with stunning precision. These machines use synchronized mechanical arms to position each candy, fold the wax paper around it using rotary folding drums, and seal it using gentle pressure rather than heat, which might soften the product. The wrapped pieces are then collated by vibratory feeders and assembled into 4-piece packs in various flavor assortments. These grouped candies are fed into a horizontal flow wrapper, where they are encased in the familiar branded packaging film. The flow wrapper uses a combination of rollers, film unwinders, photo eye sensors for alignment, and end-sealed jaws to create hermetically sealed packages that protect the candy from moisture and oxygen. The film is often reverse printed with branding, nutritional information, and batch tracking codes. Nitrogen flushing may be used in some production lines to displace oxygen and extend shelf life. After packaging, each unit passes through metal detectors and X-ray scanners to ensure there are no foreign objects or contaminants. Vision inspection systems verify print clarity, package seal integrity, and correct product count. Random samples are pooled for manual inspection by quality control technicians who assess texture, flavor, intensity, size, and appearance. Finished goods are then loaded into cartons by robotic case packers and labeled with lot codes for traceability. These cartons are palletized by robotic arms equipped with vacuum grippers, stacked in strategic configurations to optimize warehouse space and prevent crushing during transport. Once pallets are complete, they are shrink-wrapped and transferred via automated guided vehicles to temperature-controlled storage areas. Though Starburst is shelf-stable, storing it in a cool, dry environment prevents oil separation, flavor degradation, and textural hardening. From these warehouses, Starburst products are shipped out via freight trucks or distribution centers, eventually reaching retail shelves in supermarkets, vending machines, and convenience stores around the world. What makes the Starburst manufacturing process particularly interesting is the interplay between artistry and automation. While the ingredients themselves are simple, achieving the exact chewiness, vibrant color, and flavor burst that consumers expect requires precision-engineered machinery, tight process control, and an unyielding commitment to consistency. The smallest variation in moisture content, mixing speed, or cutting pressure could result in a piece that's too hard, too sticky, or aesthetically flawed. Despite being a candy rooted in simplicity, the industrial complexity behind Starburst underscores the broader evolution of confectionery manufacturing. Today's production lines incorporate real-time analytics, inline spectroscopy for flavor consistency, and even machine learning algorithms that predict equipment maintenance needs to avoid downtime. Some newer factories are experimenting with plant-based colorants and sustainable packaging materials, aiming to meet consumer demand without compromising on quality. There's even ongoing research into using recycled steam and closed-loop water systems to reduce the environmental footprint of candy production lines like those making Starburst. Mentos were first created in the early 20th century and gained global popularity due to their unique texture and intense flavor. The combination of a crunchy outer coating and a chewy interior is what sets them apart, and achieving that contrast requires precise formulation and processing. The base recipe revolves around sugar, glucose syrup, hydrogenated coconut or palm kernel oil, gelling agents like gelatin or modified starches, natural and artificial flavors, food-grade colorants, and glazing agents such as carnauba wax. Depending on the variety, mint, fruit, cola, or sour, the flavoring system will differ, but the core production mechanics remain largely the same. Production begins with the sourcing and handling of raw ingredients. Sugar is delivered in bulk form, typically refined cane or beet sugar, and stored in large silos within the factory. Glucose syrup, derived from enzymatically treated cornstarch, arrives in insulated tanker trucks and is stored in jacketed holding tanks to keep it fluid and at the proper viscosity. Oils are stored in temperature-controlled containers to maintain consistency. Each of these raw materials is subjected to a series of pre-checks. Sugar is tested for grain size and moisture content, glucose syrup for dextrose equivalent values, and oils for peroxide levels and stability. The factory's quality control department samples all incoming ingredients and verifies their compliance with specifications using chromatography, spectroscopy, and other chemical assays. Once approved, the first step in making Mentos centers on the formation of the candy core. Unlike many confectionery items, the chewy center of a Mentos is not extruded or cast, but formed using a process called compression or tableting. But before compression can occur, a slurry is created by blending sugar, glucose syrup, and oils in large mixing kettles equipped with paddle agitators. This mixture is partially cooked to evaporate water and develop the candy's elasticity. Once it reaches the desired consistency, typically with a Brix reading of about 85% solids, it is transferred to a cooling table where it is kneaded to achieve the ideal texture. The cooled mass is then broken into chunks and fed into a granulator, which reduces it into fine, uniform particles suitable for compression. These particles are sieved to ensure consistent particle size, which is critical for proper tablet formation. A binding agent, often modified starch or gelatin powder, is then added to help the particles fuse during compression. The powdered base is then fed into rotary tablet presses, high-speed machines equipped with stainless steel dies and punches that compress the powder into uniform cylinders. Each tablet is subjected to high compression force to achieve the dense, elastic core that is characteristic of Mentos. These presses can produce thousands of tablets per minute, and they feature real-time monitoring systems to ensure weight, hardness, and thickness are within specifications. The freshly compressed tablets are soft and not yet glossy. At this stage, they are known as centers and will undergo further processing to become the finished product. These centers are now ready for the panning stage, a method of coating used to apply multiple layers of sugar and flavor to build up the candy shell. The panning process takes place in large, rotating stainless steel drums called coating pans or Drageses pans. The cores are loaded into the pan, which rotates at a controlled speed while fine sprays of syrup, flavor, and color are applied in successive passes. Initially, a syrup consisting of dissolved sugar and glucose is sprayed onto the tablets using atomizing nozzles. Hot, dry air is simultaneously blown into the pan via air ducts, which rapidly evaporates moisture and causes the sugar to crystallize onto the surface of the tablets. This process is repeated over and over, sometimes more than 30 times per batch, to gradually build up the characteristic crunchy coating of Mentos. During these cycles, food-grade colorants and additional flavoring agents are also introduced. Different panning cycles are used for mint and fruit flavors. For example, mint Mentos typically receive a higher concentration of menthol and peppermint oil in the outer layers, while fruit Mentos require individualized flavor additions like strawberry, orange, and lemon, each blended with acidulants such as citric or malic acid to amplify the taste. Achieving uniform coating thickness, color distribution, and surface smoothness requires expert control of several variables: syrup viscosity, pan speed, airflow rate, and ambient humidity. Most modern Mentos facilities use programmable logic controllers and environmental monitoring systems to automate these parameters and ensure repeatability across batches. The entire panning process can take several hours, as each layer must dry before the next is applied. Operators use inline sensors and visual inspections to check for surface integrity, ensuring that no rough spots or cracks appear as the coating thickens. Once the desired shell thickness is achieved, the tablets undergo a drying and stabilization phase in climate-controlled holding rooms. Here, they rest for several hours, allowing residual moisture to equalize and the structure to firm up. The next step is polishing, a critical final touch that gives Mentos their trademark shine and smooth finish. Tablets are reloaded into specialized polishing pans and treated with a mixture of glazing agents such as carnauba wax and microcrystalline wax dissolved in ethanol or isopropyl alcohol. As the pan rotates, the wax mixture is sprayed lightly onto the surface of the tablets and then buffed by friction as the candies tumble against one another. This step not only enhances visual appeal, but also serves a functional role, creating a moisture-resistant barrier that extends shelf life. After polishing, the finished candies are cooled again to harden the glaze and prevent sticking. They are then conveyed to the packaging area via vibratory conveyors and sorting belts that align them into consistent orientations for loading. Modern Mentos factories use high-speed flow wrapping machines capable of packaging dozens of rolls per minute. The individual candies are fed into paper or plastic film wrappers, which are then heat sealed and crimped into the familiar cylindrical Mentos roll. These rolls are typically grouped into multi-packs or display trays using robotic case packers and then passed through labeling stations where batch codes and expiration dates are applied using inkjet or laser printing systems. To ensure food safety and quality, each roll passes through a series of automated inspection stations. X-ray machines and metal detectors scan for foreign objects, while vision systems inspect label placement, roll integrity, and seal quality. Statistical quality control sampling is performed by trained technicians who manually test rolls for chewiness, coating hardness, gloss level, and flavor profile using a standardized scoring system. Any deviations trigger a hold on the batch and a review of equipment calibration and ingredient records to pinpoint the source of variation. Pallets of Mentos rolls are finally shrink-wrapped and transferred to the factory's finished goods warehouse, where they are stored under tightly controlled temperature and humidity conditions. Though Mentos are relatively shelf-stable, proper storage conditions ensure they retain optimal flavor, texture, and appearance for months. From there, the products are distributed through regional logistics hubs to retail outlets around the globe. While consumers might simply pop a Mentos into their mouth without much thought, the reality is that each piece embodies a tremendous amount of behind-the-scenes engineering. From the uniform density of the core to the microscopic layering of sugar shell, every step in the process is fine-tuned to ensure consistency at massive production scales. Advanced data analytics platforms are increasingly being used in Mentos factories to track machine performance, ingredient variation, and environmental fluctuations, helping operators predict and prevent quality issues before they occur. The candy's production is also seeing innovations aimed at sustainability, including the use of biodegradable wrappers, energy-efficient panning systems, and closed-loop water recycling technologies. Some manufacturers are exploring plant-based gelling agents to create vegan-friendly versions of the product, expanding the Mentos appeal to a broader market while keeping the signature experience intact. The story of Skittles production begins with the sourcing of raw ingredients. The core of each Skittle consists primarily of sugar, corn syrup, and hydrogenated palm kernel oil, combined with fruit juice concentrate, citric acid, natural and artificial flavors, and gelatin or a plant-based gelling agent, depending on the variety. Food colorants such as Red 40, Yellow 5, Blue 1, and others provide the vivid, rainbow-like appearance, while carnauba wax is used for the final shine. All ingredients arrive at the factory in bulk, sugar in pneumatic tankers or super sacks, corn syrup in heated tank trucks, oils in insulated totes, and flavors and colors in sealed drums to preserve potency and prevent contamination. Once the raw materials are delivered to the facility, they undergo quality inspection. Sugar is tested for purity and grain size using optical sensors and moisture analyzers, while corn syrup is evaluated for its dextrose equivalent to ensure consistent sweetness and viscosity. The oils are checked for oxidative stability and melting point, and flavor compounds are tested with chromatography to confirm identity and strength. Approved ingredients are then routed to ingredient storage silos or intermediate tanks, each connected via stainless steel piping to the central mixing systems. The production of Skittles begins with the creation of the chewy center, which is not molded or extruded like many other candies, but rather formed through a process known as casting or deposition. First, sugar, corn syrup, and oils are combined in large, stainless steel, steam-jacketed kettles. Agitators mix the contents while the batch is heated to around 115 to 120 degrees Celsius. This heating step is critical. It dissolves the sugar, reduces viscosity, and activates the gelling agents that will give the Skittle its characteristic chewy texture. Once the mixture reaches the desired consistency, it is partially vacuum cooked to remove excess moisture, yielding a thick, elastic syrup. This candy mass is then deposited into starch molds, which are pre-formed trays filled with cornstarch that contains indentations for each candy. Depositing heads, essentially nozzles controlled by servo-driven pumps, release precisely metered amounts of the syrup into each cavity. These molds are then transferred via conveyor into a climate-controlled drying tunnel where they remain for 24 to 48 hours. During this time, water evaporates slowly and uniformly, and the chewy texture begins to set. After drying, the starch is separated from the candy cores using a destarching system. This equipment gently shakes and brushes off the remaining starch, which is collected, filtered, and reused in future cycles. The now formed Skittle centers are tumbled in large rotating drums to smooth their surface before being passed to the next critical step, the sugar shell coating, also known as panning. Panning is a cornerstone of Skittles production and one of the most technically demanding phases of the process. The centers are placed into enormous rotating pans, typically several meters in diameter, where the sugar coating is built up through dozens of thin layers. Each pan spins continuously, and while it does, a fine sugar solution is sprayed onto the candy centers. This syrup typically consists of refined sugar, glucose, water, and sometimes citric acid for tartness. Immediately after spraying, a blast of temperature and humidity-controlled air is directed into the pan, drying the surface and forming a thin, hard layer. This coating process is repeated many times, sometimes for several hours, depending on the desired shell thickness. Different flavor syrups are added at different stages if multiple fruit profiles are being used within the batch. The rotation speed, spray volume, airflow rate, and drying temperature are all managed by PLC-controlled systems that monitor pan performance in real time, ensuring consistency in shell formation. Operators oversee the process via touchscreen HMIs, adjusting parameters based on real-time data and sensory feedback from test samples. Once the shell has reached its final thickness, color is added. This is typically done with 1 or 2 additional layers of tinted sugar solution, each one custom formulated for a specific flavor variant. Red for strawberry, yellow for lemon, green for lime or apple, purple for grape, and orange for naturally orange. These solutions include FDA-approved food dyes, stabilized with acidulants and emulsifiers to ensure even distribution and adhesion to the candy surface. The result is a batch of candies, each uniformly colored, with a bright and durable outer shell. Next comes the finishing stage, where Skittles are given their unmistakable gloss. This is achieved using polishing pans and a mixture of carnauba wax and microcrystalline wax, sometimes diluted in alcohol to aid dispersion. The candies are tumbled gently, while a fine mist of the wax solution is sprayed onto them. As the pan rotates, the candies polish each other through friction, creating a smooth, shiny finish. This step also provides a moisture barrier that helps extend shelf life and prevents the candies from sticking together in the package. After polishing, the Skittles are passed through cooling tunnels to solidify the coating and stabilize the structure. Then comes the critical stage of flavor sorting and portioning. High-speed sorting machines equipped with optical sensors separate the candies by color, using burst air jets to redirect them into designated channels. This ensures that each bag or pack of Skittles contains the full assortment of flavors in consistent proportions. The sorted Skittles are then conveyed to packaging stations, where they are portioned using volumetric or weight-based fillers. Each batch is dispensed into the appropriate packaging format, whether single-serve pouches, resealable share bags, or rigid tubes. The packaging film is reverse printed with branding, nutritional information, and traceability codes, and it is fed into horizontal or vertical form-fill seal machines. These machines form the pouches, fill them with product, and seal them in one continuous motion. Precise temperature and pressure controls ensure that the seals are airtight without melting the product inside. As the packaged Skittles exit the line, they are subjected to a series of inspection checkpoints. Metal detectors, X-ray systems, and vision scanners verify that each package contains the correct amount, is sealed properly, and is free of contamination. Random samples are pulled for quality testing, evaluating chewiness, shell thickness, flavor strength, and visual appearance. Some factories even use texture analyzers and sensory panels to verify that the candies meet brand specifications. Once approved, the packages are collated into cartons using robotic case packers and then palletized by automated stacking systems. Each pallet is stretch wrapped for stability and labeled with tracking information, including production time, line number, and batch code. Pallets are then routed to the warehouse, where they are stored in temperature and humidity controlled conditions to maintain optimal product integrity. Skittles are remarkably shelf stable, but proper storage conditions ensure that the texture remains soft and the colors do not fade. From the warehouse, Skittles are distributed via truck to retail distribution centers, grocery stores, vending machines, and online fulfillment facilities. The journey from raw ingredients to store shelves is timed to ensure freshness and consistency, with sophisticated supply chain software tracking every shipment to maintain inventory and respond to fluctuations in demand. The production of Skittles is not only an example of precision manufacturing, but also one of mass customization. Despite being produced in colossal quantities, every single piece must conform to strict standards of flavor, size, color, and texture. Innovations in data analytics, predictive maintenance, and machine learning are being introduced into Skittles factories to continuously improve yield, efficiency, and sustainability. Energy-efficient drying systems, water reclamation units, and biodegradable packaging research are helping the brand minimize its environmental impact without compromising the product's appeal.